All right, good afternoon, everybody. So I hope you all had a relaxing break and relaxing time off from Tuesday's lecture. I want to quickly remind everybody before we begin that the first co-review, make sure that you've coordinated with your project manager and that you coordinate your meeting with your project manager to set up that process of going through, seeing what you actually accomplished, what you thought you'd have accomplished to this point. And then what your project manager will do is walk you through the process of reassessing any risks, seeing what challenges you encountered through the first week of working on this project, and apply spiral software development. It's often also known as agile development, being able to make sure that you're constantly reassessing the challenges that you have faced on the project as you move forward. And that's how you apply your knowledge of data structures, not just for the rest of the semester, but what you're going to be doing through the rest of your careers. By being able to weigh those challenges of space-time and runtime complexity, and being able to figure out what works best with what it is that you're trying to design, that's where you can really strengthen your knowledge of data structures and being able to apply them as you go out into industry. So today what we're going to do is we are going to cover, I see we have a comment in the chat. All right, whoops. All right, so we have a comment in the chat. Please, what we're going to do is we're going to cover a new data structure called a red-black tree. And we're actually going to be spending today's lecture and next Tuesday's lecture on it. It's a combination of almost everything we've learned up to this point. And we're going to learn more about what's known as relaxed balance. How can we get a good enough version of log n of find, search, and insert without gaining some of the overhead in terms of balancing mechanisms that we gain from AVL trees, and also being able to maintain this binary node that we've used so far with binary search trees and AVL trees that gets away from this B tree idea where we're having several values in a node. The first thing I would like you to do is I would like you to take 5 minutes and work on problem one. The short link, when you follow it, B, uppercase U and G will take you to the final exam review page. And specifically, when you click on that link, it will take you directly to lecture 22. And the two problems that we'll work at on the whiteboard are already there. So you can look at the type of thing and the way they would be presented on an exam. Problems 3, 4, and 5 will be coding. We'll be working through coding a red-black tree node, and we'll be working on insertion today. And next Tuesday, we're going to work on deletion. So please take time to work on that problem. And it's make prob 1. As always, you're welcome to discuss and ask questions in the Slack. So while you're finishing up, I will quickly share an email that I just got from Professor Kuala Tuang, who is actually mentoring the drone state and drone flight pre-internship teams. She sent an email and asked me to share with all my students the summer internship that she runs. Specifically, it'll be June 2nd through July 30th. And basically, you get $6,800 stipend, any current Notre Dame students with preference for CSE, that's you obviously. Good at building, assembling physical objects, team player, Linux, our real-time operating system. So those of you who have some familiar experience with that, that is a paying summer opportunity for you right there. So if anybody has any questions about it, I will be happy to discuss with you after class. So what I would like to do next is I'm going to go over and we're going to work through problem 1 together on the whiteboard over here. And I want to point out on the exam that there will be 2 B-tree problems. One will be a degree of 3 and one will be a degree of 4. So when you see the video that I have for this problem, you're going to notice that I work through it in both a degree of 3 and a degree of 4 example with the exact same insertions and deletions, with the objective of helping you see how both of those will work. So how are the first 3 insertions going to look here? Let me rephrase. How are the first 4 insertions going to work? What's it going to look like? Any ideas? Somebody certainly at least attempted the problem, right? Yes. Absolutely right. So what's happening is we initially put in 1, 10, and then 2. So it'll initially look like 1, 2, and then 10. And what happens is we're going to put in 9. So if you put in the order, 9 would go here, right? So what's going to happen is this one's going to come up. And what we're going to see today in our discussion of red-black trees is why it's important for that specific element to rise. So what will happen is, let me get my eraser, is 2 will rise up. 1 will be the left subchild, and then we're going to have 9 and 10 over here. So now what we're going to do is we're going to insert 3. So what should happen now? Anybody? Yes, in the back. Very good. So it's going to go in the right subtree. It's a degree of 4. So it goes here, 3, 9, and 10. So now we're going to insert 8. So what's going to happen here? Yes. Very good. So what happened, well, it's going to send, here we have 3, 8, 9, and 10. So 8 would be here in the order. So what's going to happen, so very close, we put 8 here, and then we would split it up. So what would actually be happening below is 8, 3, 9, and 10. But because we have an extra space here, 8's going to come up. 3 will be here as the second child, and then the third child will contain 9 and 10. All right, so now we're going to insert 4 and 7. So what's going to happen here? Can anybody tell me the result of the tree with a degree of 4 here? Yes. Very good. So 4 goes here. And what about, and you're right, so it's 4 and 7 will both go here. So now when I do 5, what will happen? Yes. Very good. So 5 would be here in between 3 and 4. We're going to raise 4 up. And because it's a degree of 4, that means we can have 4 pointers, 4 children with 3 values. So this subtree, when we insert 5, it would look like 3, 4, 5, and 7. So what will happen is we're going to raise it up 4. This would move over here. We'd have 8. 9 and 10 would be over here. And then 5 and 7 will end up over here, like so. And we have one last one to insert, which is 6. And so 6 will end up here. 5, 6, and 7. Does this make sense so far? On the exam for the degree of 3 and the degree of 4 problem, you know you're on the right path if the first value you see here in the delete is in the root node. So if you see that, you're on the right path. So far, so good. And we see here that that has in fact happened, that 8 is here. There's some sort of really annoying animal above me right now, but that's okay. So how are we going to delete 8? What should we do here first? Yes? Yes, so what's going to happen is, because we have enough elements, we're going to move the largest element to the left, which in this case is 7, up. And then finally, we're going to delete 4. So 4 comes here, and that's going to be gone. So here's the way that the red-black tree will work through this process. So when you're studying it, you go through the animation, here's what the animation will do, and here's how it's coming up with this. It's going to do the same thing. It's going to look to the left and see if there's a value that's less. So in the animation, you'll see it bring up 3, and you'll see an empty value here. What will happen next is it's going to look to the right, the next child over, to see if we have more than one value, which in this case we do. So what's going to happen is it's going to go, oh, hey, I'm going to take the smallest value to the right, move that up, and I'm going to move the value back down. So it actually ends up like this, 2, 5, 3's down here, and then 6 will end up by itself. And if I remember correctly, this is choice C. Does anybody have any questions about anything I did there? You do have a question? No, this is for a B tree. Yeah, we're about to dive into red-black trees. So the interesting thing about this, and actually the question you have ties in, dovetails really well with what I'm about to discuss, is that in the innovation, so red-black trees were invented in 1972. And we're trying to get around AVL trees. B trees has been a good solution. It works really well with databases. So for those of you who take Professor Bolalin's databases course or Professor Wenninger's advanced databases course, you're going to see B trees and then a more advanced version called a B star tree, I'm sorry, B plus tree. And that will be a big foundation of how databases work. But we wanted to revisit and figure out the solution to this initial problem, which is how do I get around the issue of this binary search tree that has a potential worst case scenario without incurring all of these rotational overhead challenges that we get with the AVL tree. But I want to maintain having one value with 2 children. So in this case, we'd have a B tree with a maximum degree of 2. And that's where the idea of a red-black tree came from. So what I'm going to do now is I'm going to show you a B tree here in the slides, except now I'm going to do so from the perspective of seeing how we can come up with a set of rules based on B trees that allow us to be able to convert back over. So let me hide this real quick. So binary search trees, as I discussed, best case scenario for insertion and deletion, but we have this worst case big O of n. AVL trees have complex balancing mechanisms. We've also talked about heaps. Max heaps and min heaps are do us very well to find this big O log of k for inserting. But the crucial thing is we use that heapify property. They're not in some sort of sorted order. So we have this worst case scenario of trying to find everything and still, if we want to determine if an element is in a heap and it's not the minimum value, it still has a big O of n time. So we talked about these local transformations that we did over here. We just presented that into the problem. And so the design choice for the B tree is it's local. We don't have to measure all of the balancing on all of the sides. So is there any way I can translate these local balancing mechanisms into something that works in a binary search tree? And that's where red-black trees come from. So let's go through and let's say we're going to relax the balancing requirement. Instead of saying that the balancing requirement is going to be that we can have no more than 1, meaning that if my max to the right is 3, it has to be 2, 3, or 4, right? It has to be very close. What happens if I say the worst case scenario is that it's twice as long as the shortest path? So if I have 6 on my right, the worst case scenario on my left would be 3. So I still have a good balance, but we've relaxed it a bit. So what I'm going to do here is I'm going to come up with using a B tree of 4, just like we did in the last problem, except what we're going to do is we have a pointer, value, pointer, value, pointer, value, and pointer. What I'm going to do here is I'm going to say, well, what happens if I were to translate this? I'm going to call this value 1, value 2, and value 3. What if I translate this into a binary search tree where I had value 2, and the pointer over here, we have value 1, and then value 3. And then I use all of these subtrees as another form of pointer. So now let's do the same thought experiment that the inventors of the red-black tree did and work through. And what we're going to do is we're going to differentiate between these. We're going to say that the one in the middle, we're going to call this a black node. And the ones on the side, V1 and V3, we're going to say that those are red. And that allows us to be able to differentiate inside of the B tree node as to which one is in the middle and higher up, and if we were to translate this into a binary search tree representation. So let's go through a small insertion, and I'm going to propose a couple of different rules. We're going to see that when I insert it, instead of saying I'm going to insert it over on the left-hand side, the first value that comes in is going to be in the middle, and we're going to denote that as a black value. So initially, when I insert 2, in this thought experiment, instead of putting 2 over here in this key, I'm going to put 2 here in the middle. Next, I'm going to put 4 in. Here's how this is going to work. 4 is going to be greater than 2, so I'm just going to put 4 over here. We haven't filled it up, so what you're going to see in the next animation is I'm going to put 4 over here, and I'm going to denote this as a red node. Does that make sense so far? So now when I insert 6, here's what's going to happen. 6, in order to fill up this key, will move everything over. So it actually become 2, 4, and 6. Now what's going to happen is 4 would be the black value, and 2 and 6 are going to be red. So what we're actually going to see is we're going to see 4, 2, and 6, like so. So by doing this, we're able to represent a red-black tree as a kind of a rotation. So watch what happens. We put in 6, and we see that it goes this way. So what we're going to say when we eventually get to the tree is we have 2 and 4 and 6. We're going to have, initially, this will be red, and this will be black. And we're going to define a rule that tells us, well, what's going on over here? How can we figure this out? If I have a red parent and a black, what we're going to say, uncle, and black nodes, pointers, null pointers are going to be considered black, we actually perform a very specific form of rotation that's very similar to what we've studied so far with AVL. And we see that in the end, we have 4, 2, and 6, but we're going to recolor them, where 4 will be black, 6 will be red, and 2 will be red. Now, for now, we see that it matches perfectly with the B tree. Does that make sense so far? So let's stick with our B tree analogy before we start introducing more red-black tree rules. So now I want to insert 10. So what's going to happen is 10 would go over here, like so. And we know that we're going to lift up 4, like we would in the B tree. And so this is a common question that I got both in office hours and during lecture. So why is it that we chose this specific one to lift up? So if I do this, what's going to happen is 4 is going to lift up, and it's going to have 2, and it's going to have 6 and 10 over here. In our thought experiment, 6 is going to be the new black node, and 10 is going to be red. 2 will be in its own node, and this will be in the middle, and it will be a black node as well. And 4 will be up here, and it will be black, because they're all going to be in the middle because they're by themselves. Does anybody have any questions on this so far? Let me throw another thing for you to think about as we're continuing to walk through this example. Notice how from any path from the root to a null pointer, we go through the same number of black nodes. That's going to be our balancing rule. We want to make sure that at the end, the number of black nodes through any path from the root to a null node in the leaf is the same. Where we're able to get that 2 times balance is having alternating red nodes. So in this case, what we see in this particular tree is to the left, I have 4 and 2. And to get to either of 2's children, I have to go through 2 black nodes, in this case, 4 and 2. If I'm going through here to the left child of 6, which is null, I go through 2 black nodes, 4 and 6. And if I want to get to any of the children of 10, I have to go through 4 and 6, so that's 2 different black nodes. The equivalent is that we would traverse through 2 B tree nodes in order to get there. Does that make sense? All right, so let's continue. Now we're going to insert in 8. So 8 would actually go here in the middle. So 8 is going to be initially a left child of 10. But to go through this B tree experiment, what would actually happen is it would shift 6 over, so it becomes 6, 8, and 10. Since 8 is in the middle, it becomes a black node, 10 is red, and 6 is red. So it's actually performing that similar type of rotation. So it's borrowing ideas from AVL tree and B tree in order to provide a simplified balance. Does what I just did make sense? All right, I'll check in the Slack just to make sure. Okay, so we have a question. Why did 2 become black when we added 10? So what's going on is in this thought experiment, every node value that's in the middle of the B tree. So this is different than a normal B tree. And a normal B tree would be in that first location. In this thought experiment, it's in the middle. So when it's in the middle, we're saying it's a black node, and then we're going to have children, which will represent red nodes. So that's why this particular node is black. So our RB tree is always degree of 4. So let me clarify, and forgive me for skimming this question, but I will dig into this a lot deeper later. A red-black tree is a degree of 2 in that it's a binary tree. However, its behavior is meant to be similar in nature to a B tree that has a degree of 4. Does that make sense? So let me, so those of you who asked those questions, please let me know if I addressed your questions. And I will follow up and clarify that answer more clearly. Does anybody have any, okay, getting some thumbs up. Does anybody have any questions for those of you here in the room? Okay, so let's continue. So now we're going to put in 9. We would lift up 8 in this case. And so what we'll see here is that we're going to split. And now, what would we do here when we split this in a normal B tree? What's the next thing that we would do? Everybody remember we actually did something very similar just now in the review problem. I'm also checking the Slack. Does anybody have any idea? So we have split and raised 8, but now we have 4. So if this was just a B tree, what would you do here? Yes. Absolutely right. We would merge 8 into the tree. And I think that's probably what I see a couple people typing on the Slack. So it would come up here and 8 would be on the right, which means that in our thought experiment, 4 is going to remain in the middle, 8 would be on the right, which means that 8 would become a right child of 4, which means we're going to say that 8 is red. So what we're going to see here now is that 8 is going to be red, so it's going to be 4. We're going to change this color here, and we see that 6, when it split, was put in the middle, so now that's black. And 10 is new, that's black. 9 is the new one, so 9 is red. And we see that when we put 9 here, 9 will become red. And in this particular case, we're going to be able to get this relaxed balance. And this is going to follow up on the question from a little earlier and meet my requirement by saying, well, if 8 comes up here and it becomes red, this is going to turn red. 10 is going to turn black, and 6 is going to turn black. Does everybody see that? So in this rule, you're just going to see that the colors are going to change. So this gives us relaxed balance. We see that on the left, the height is 2, but it goes through 2 black nodes, 2 and 4 and then 2. To get to any null pointer on this right-hand side, we see that here we go through 2, here we go through 2 black nodes, and here we go through 2 black nodes as well. So does that make sense to everybody? I do see that there's a question being typed in the Slack, and I'll address it in a moment. So now we're going to insert 14. 14 is going to be to the right of 10, so we're going to see that 14 becomes a red node in using our modified B tree. So now we're going to insert 11. So what's going to happen is 10 in this case would be lifted up, and it would be lifted up here. So 11 would initially be here. And we're going to see that 10, 9 is going to be over here. We're going to have 11 and 14. 14 is going to become black. I'm sorry, 11 is going to become black. 14 is going to become red. 10 will initially be black, and 9 will initially be black. But now it's coming up here. We're merging this because we still have an empty value. So what's going to happen here is we're going to see everything move over. All of these pointers are going to move. We're going to see this pointer is going to move here. We're going to see that 4 moves here. This pointer will move over. We're going to see 8 comes in the middle, and then 10 is going to come over here. This is what we're going to call a double right rotation, somewhat similar to AVL tree. In the end, by having this, what we're going to see is that 8 will be in the middle, and that will be a black node. 10 will be on the right, and will be red. 4 is going to become red. And everything else that we've drawn out will remain the same. So it's going to look like this. It's going to merge up. And that is our final thing. We see that here in the B tree representation, all of the leaves are on the same level. And the leaf here for 11 and 14 is here. 9 is here. 6 is here. And 2 is here. Then the root key contains all of these values. There's 2 questions in the Slack. Before I get to them, does anybody in the lecture hall, does anybody have any questions? All right, so let me get to the 2 questions in the Slack. The first question is, so are we reordering and then changing the colors? That first part is yes, and we'll go into a lot of detail about the rules and how that's done. Or is it better to guess? Now, we're going to have a very strict set of rules to do that. So the first thing that your first proposed solution is the correct one. And what is the rule that you made to bring 8 up? So this is going to be very similar. Let me go to the previous one. So 8's already here. We are bringing 10 up. And the only difference is if this was a normal B tree, we'd have 4, 8, and a blank spot. In this case, we have a blank spot, 4, and 8. So in this case, these move over, and then 10 becomes the right child. So please let me know if those addressed your questions. All right, so we inserted 11, then we do 5, and then 7. And we see that by using this, we can just quickly insert those values and not have to worry much about anything. And so the idea behind a red-black tree is it's using this same kind of balancing idea that we have in B trees, but taking it and turning it into a binary search tree. So here is how the red-black tree works. So the red-black tree, we use locality of relationships. We're going to come up with several rules for insertion and deletion. A red-black tree is a binary search tree where every node is either red or black. The root and all null pointers are defined as black nodes. So we see that I have an example here on the right that's In this case, the root is 8, and it has a path to the left of 5. It has paths here and here. And the major rule that we're going to see is that any null pointer, to get from the root to a null pointer, goes through the same number of black nodes. When we insert a value into the red-black tree, we have to initially define it as red. And we're going to see that as I go through all of the different examples. So here, to map what I have in this tree to the definition I presented on the previous slide, the root is a black, and that's the value 8. That's a black node. 9, 13, and 23 have null children. We technically will consider those as black. 12 has 2 children, 9 and 13, that are red. 19 has null and 23. 15 is a red node and has 12 and 19. A red node may not have another red node as a child. And what we're going to see is that when we insert it, it will initially create those scenarios, and then we are going to use our balancing rules to fix them. All right, so quickly I want to just go over the math to justify our claim. So what we're going to have here is we are going to say that at least half the nodes along any path are black, right? So when we say this path, there's 4 nodes, 2 of them are black. On this one, we have 3 and 2 of them are black. So at least half. So therefore, we're going to call this the black height, BH. So the black height is at least half of the height from the root. So the height of this tree is 4. So therefore, we can say that the black height goes through 2. So it's at least 2. And so when we say this, now we're trying to figure out how high the tree will actually be. So when we figure this out, we're going to say that n minus 1, or n plus 1, excuse me, was greater than or equal to the black height of the root. So we do a logarithm. And now we have that 2 to the power of the black height from the root minus 1 is going to be less than the actual height of the tree. And when we solve this, we get 2 times log of n plus 1. And so that is our quantification of this relaxed balance. In an AVL tree, it's no more than 1 on either side. Here, by allowing us to have red nodes and using this idea from B trees, we are able to get a relaxed balance. The goal is that we can get a generally good representation of log and insertion and find that may not always be the best, and we're going to see examples where red-black trees can have issues. But in general, this will allow us to you have something that is more usable than an AVL tree. And what we'll see on Tuesday is that the foundation for a lot of data structures and standard template libraries that have a tree-like structure will use red-black trees for that exact reason. So standard set is a red-black tree. Standard map is a red-black tree where we sort by the keys, but you can have values. So it kind of combines the idea of mapping with an unordered map, but then we have a red-black tree to reduce memory that we would gain from the worst case scenarios of the hash table. And so here, just to combine some concepts from earlier this semester, we saw that G of n, in order to figure out the big O runtime, that we had a constant starting at a specific value. So in this case, 2 times log of n. We just say that, well, if C is 3, and for L values greater than or equal to 1, excuse me, we can then claim that red-black trees operate in big O of log n, insert, find, and delete. All right, does anybody have any questions about that? Let me check the Slack to see if there have been any questions. All right, so let's start working through some rules then. A quick historical note, common question, why is it called red-black tree? So when Robert Sedgwick was working at Xerox and invented red-black trees. He, of course, is working at Xerox, so they have the innovations in printers. And at the time, they had just invented laser jet printers. And so he's printing everything out and trying all the new fancy colors. And the two that he thought made it look the best were red and black. So that's why red and black were picked that way. All right, so getting started with insertion. When we insert a node into a red-black tree, the first thing that's going to happen is it's going to go down to its normal location as if it were being inserted into a normal binary search tree, and we are going to define its color as red. Does that make sense so far? So automatically it's going to be red. Then what we're going to do is we're going to perform localized evaluations of all of the different colors of its neighbors. And what you're going to see is we have to count for its parent, we have to count for its grandparent, and we have to account for what we're going to call its uncle. So its parent sibling. Now, can anybody think, if we go back to our binary search tree node definition, what were the pointers that we had in that particular node? Does anybody remember? Yes. Left and right, very good. Just left and just right. So if I'm here, if I have a pointer pointing to this specific node and I know this way and this way, what's a potential issue if I'm trying to figure out parent, grandparent, and uncle? If I'm trying to perform an evaluation here, what is the big issue? Let me give you a polite nudge in the right direction. How would I know where my parent is if I'm a red-black tree node? If I only know where my children are, how would I find out my parent? Any ideas? Yes, in the back. Yes, so we got to figure out another way to figure out how to point to the other node. I see that there's something being typed up as well. So what we're going to do is we're actually going to have 3 pointers. We're going to have left, right, and we're going to see that we're going to have a parent. And one of the things that we're going to write up is a method to determine whether something is a sibling or whether something is an uncle. So we have to figure out how to get all this information. So once I go here, I can just go in the opposite direction and figure out the color of the sibling node. So the first rule is case 0. If the root node, in this case we're going to call it grandparent, if it's red, just change it to black. And this will work because any path after the root, if it has n black nodes that it goes through, if it's properly sorted, if I add a value, if I make the root node black, it will just add 1 to every path. So therefore, we want to make sure that the root node is always recolored to black every single time. This would be like when I insert a value into that B tree node, it goes into the middle and that becomes black. Next thing, case 1. So in case 1, the child is inserted and it has a red parent and a red uncle. So what we are going to do is we're going to recolor. So I showed that example a little earlier when I moved everything over into the B tree node. What's going to happen if you have a situation where the parent is red and the uncle is red, we just recolor the parent, uncle, and grandparent. So you're going to see in the animation, parent will become black, uncle will become black, and the grandparent will become red. So now we don't have to do a rotation because any node in this subtree will go through the same number of black nodes. And then to clarify, this is a common question that I get. So, well, I guess I took it out. Normally what happened in this case 1 is if you bring back up here, and let's say the grandparent is the root, what would I do here? If the grandparent in this scenario, I've recolored and now I come back up, what's the last step I need to do for the grandparent? Yes. Turn it black, absolutely right. So this would become a black node. So case 2, it's the same as case 1, except now the uncle is black. So we're gonna have a parent is red and uncle is red. So I apologize here for some reason. Here, let's say our parent is red, except the uncle is black here. So what we're gonna do is we now know the ordering of parent, child, grandparent, and uncle. So if this was 10, this would be 7, this would be 8, this would be 12. So the grandparent is 10, parent is 7, child is 8, uncle is 12. And so we now know that the ordering is parent is less than child, is less than grandparent, is less than uncle. Does that make sense to everybody so far? So now what we're going to do is we're going to perform a rotation. So we did something very similar where we're just going to see child come up, and then it's going to be grandparent. We see here child left is going to become the parent. It's going to point to parent, and then grandparents left is going to point to child. So grandparent's going to be here, child would be here, parent would be here, and uncle is here. So the big thing about this configuration is it's going to take us to case 3. And the reason why is because child is red and parent, the original parent is red and the original child is red, and we can't have a red node be the child of a red parent. Does that make sense? So we're going to perform that rotation very similarly to what you've done with AVL trees. And then that's going to take us to, okay, so here's that animation. Let me skip through this, blah, blah, blah. All right, case 3. What is going on with my animations? All right, I'll just work through this. All right, so what's going to happen here is that the red node that we insert is the left child of the parent, and we have a black node here. So this is what we concluded case 2 with. So what's going to happen here is we now know that the grandparent is black, the uncle is black, and the parent is red. So what we had before, we initially had grandparent, parent, child, and uncle. Then we performed this rotation, and this became grandparent, child, parent, and uncle. Child and parent were originally red. Now we move to case 3. And in that representation, we're going to say that this is now the parent and this is now the child. So now we have to figure out how to fix this. So now what we're going to do is we're going to recolor the original parent and the original grandparent. So what we're going to see here, we're going to perform this rotation, and we're going to move grandparent down. So we're going to see here that parent, grandparent, and uncle will be here. Child will be moved up, and we'll be able to maintain the coloring. So first, let me go through an insertion example, and then I'll do an animation example with you, and then we'll work through a problem together. So first, I insert 10. All nodes are initially inserted as red. Then we're going to change that to black. Yes? No, you must insert every node as red because you have to insert at the bottom and then perform the rules. Otherwise, you're going to have all kinds of other issues. So if you want it on the exam, obviously, for space, for time complexity, you obviously will just say, well, that's a black node, obviously. But in this case, we must insert it as red because as the tree gets bigger, that's how we're going to initially be able to identify where our balance is. So before, I'm going to go through all the cases, but we have to perform rotation. So I'm going to tell you which case we encounter. So initially it's red, then we do black. Then we insert 15 as red. We don't have anything in terms of grandparents and uncles right now, so we don't have anything we need to do. Now we're going to insert 25. So what's going to happen here is we have case 3. So what we're going to do is we're going to say, all right, I'm going to rotate. 15 is going to become black. The child is going to stay red, and the grandparent is going to change color. So this is case 3, where we rotate and change the colors. Right, so we see here it makes the right child of 10 point to the left child of 15. The left child of 15 rotates. It moves over. Then we recolor the original parent and the original grandparent. The original parent was 10. The original grandparent was 10. The original parent was 15. So now they are recovered. So now we've hit that case 3. Does everybody see that? All right, so now we're going to insert 12. So now we hit our case 2. So for the question in the Slack, can you go over case 2 again? Here we go. For case 2, we have the instance where we have the parent is red and the uncle is red. This actually might be case 1. I'm sorry. Yeah, this is case 1. My apologies. I'll get to case 2 in a moment. I know there's a case 2 in here. So what's going to happen is we're going to see in case 1 that the uncle is red and the parent is red. So what we're going to do is we're going to recolor the parent, the uncle, and the grandparent. So 10 and 25 are going to become black, and 15 is going to become red. Then, and to get to the question that was asked before, we will get to the top and we will recolor 15. So we want to be consistent in our algorithm, which is why we're always initialize everything as red. So that way that same process, when we encounter it, will be done over and over again. All right, now we're going to insert 5. So right now, we don't have any issues with the parent or our uncle, so we're good. Now we're going to insert 4. Now we're going to recolor 5 and 12 and 10. So this is a case 1, and we're going to see that when we recolor them, that we now have the same number of black nodes between each path. Right? And so another thing, we have our relaxed balance. We see that there's 4 on this path, 2 on this path, so it ends up working out. All right, so now we have a scenario in which 3 has been inserted. We have 4 as its parent. We have 5 as the grandparent. And now we have a null pointer as the uncle. And this is why it's important to indicate that null pointers are black, because this allows us to be able to relate it to our rotation rules. So in this case, what's going to happen is we have 2 red pointers here, and 2 red nodes here, black grandparent, and now what we can do is this becomes our case 2. So this now I'm going to address the question in the Slack. So what's going to happen is the grandparent, which is 5, its left child, which we see as the blue arrow, points to the parent's right child, which in this case is null. Then the parent's right is going to be pointing to the grandparent. And then the grandparent's root node, this is going to be the parent. So now what's going to happen is we're going to move this over. We now see that 10's left child is now pointing to 4. So let me go back so that way I can address this question in the Slack more clearly. What is going to happen is we have the grandparent is 5, parent is 4, child is 3. We have these nodes red, red, and black. And the great-grandparent is 10. So what's going to happen here is that 4 is pointing to something. 5's left child will initially point here. 4's right child now, for case 2, is now going to point at 5. 10's left child, which originally there, is now going to point here. So now we're going to get that kind of rotation. Does that make sense? So now let's go through the animation. We now see that we have this here. And then to the last thing we need to do, we are going to recolor 4 and 5, like so. So please let me know for the student who asked me about case 2 in the Slack, if that addressed your question. So what we had there is we had a parent and a grandparent that were on the same direction. I'm sorry, I was about to say zig zig, and I realized we haven't covered splay trees yet, so I don't want to throw terminology you're not familiar with yet. Now we're going to insert 2. Now we have a scenario where the red node is inserted, the parent 3 is red, and the uncle 5 is also red. So now we have ourselves a case 1. And now we're going to recolor. So we recolor. So let me go back just because I see some of you taking notes. We're going to recolor 3, 4, and 5. Parent, uncle, and grandparent all get recolored. So we're going to see that 3 and 5 become black and 4 becomes red. What is the issue with this? What's wrong with my tree now? Yes. Absolutely right. We cannot have a red node be the parent of another red node. So now we're going to evaluate this. And from this, we have grandparent, parent, child, and uncle. Does anybody recognize which case this is? I'll give you a hint. We just went over it. There's case 3. Yes. We're going to do case 2 here. So in case 2, this is where we're going to perform a rotation. On your exam, there will be a rotation like this where you will be expected to identify when you change the color that you have to do another rotation. If you see this, now we got to do a rotation here. So we're going to do the same thing. We have the root pointing to 15. What's going to end up happening? We're going to move 15 down. The root's going to become 10. 10's right child is going to become 15. 15's left child would become 12. And then after that rotation, we're going to see the new coloring. We had case 2. We identified the pointers. And now we're going to rotate. And we now see that we have this tree. What was the very last step of case 2 after we performed the rotation? Does anybody remember? Yes, in the back. Yes, for case 2, we have to recolor. 10 becomes black. Very good. So 10 and 15 switch. I see that also in the Slack. So both of you got the answer correct. We recolor 10 and 15. So that was the last step of, so this was the previous, and that's part of case 2. In this case, we would actually evaluate again whether or not the root needed to be recolored. In this case, it doesn't because 10 is already black. All right, so what I would like you to do is I want you to work through problem 2. Problem 2, run make problem 2. Take 5 minutes, we'll take 4 minutes, and then we'll work through it together on the left board. We're inserting 20, 10, 30, 25, 35, 26, 27, and then 28. And work through, red-black trees are notoriously challenging to get your head around the first few times you work on them. So if you're working through this and you get stuck, identify that as your opportunity for study. Say, okay, I couldn't quite figure out which particular case is what. It's perfectly okay to struggle with this problem at first. And likewise, you're always welcome to discuss on the Slack if you have any questions. All right, so what is the very first step? Get out my red marker and my black marker. What's the very first step? Nikita, I'm going to pick on you because you asked about this. So very first step, what should I do here in the red-black tree? And I'm inserting 30. But, okay, so the very first step is we're just going to insert 30 and make this a black node. I'm picking on you because technically it's inserted as red and becomes black, but on an exam, make it simple, we'll put in 30. Next, we're going to insert 10, right? So 10 is initially going to become the left child of 30. So now we're going to insert 20. 20, all nodes are initially inserted as red. So what is going to be going on here? What do you think the rule that I should apply should be? Yes. Right, we're going to do a rotation. So what happens is we have a black node as an uncle. So what's going to happen here is we're going to take that first step and we're going to see that 30 is going to stay here. And now we're going to move from case 2 to case 3. So we're going to have 20 and 10. And so now we're going to do what Nikita said, we're going to do a rotation. So now we're going to rotate like so. And this is now going to become, 20 is going to become the root. So the way the rotation works is 20 will initially be here, 30 will be here, and 10 will be here. What's the last step? Let me check the Slack to see if anybody is suggesting anything or asking questions there as well. What's this next step? I have one last thing I need to do at this particular stage before I continue. Yes. Very good. We need to recolor. And so 20 is going to become the new black node. And 30 is going to become the new red node. So far, so good. Outstanding work. So now we're going to insert 25. 25 would become a red node to the left of 30. So what's our issue here? What would be the case here? Yes. Very good. So what we're able to do is we can recolor. So 20 would become red, 10 and 30 would become black. And now we're going to go from case 1 to case 0. Our root is red, and now we recolor it. So now we have 2 black nodes on every path to every null pointer. Now we're going to insert 35. And we can leave this alone. We don't have to mess with it at all. The next thing we're going to do is we're going to insert 26. So now I would put 26 here. So what do you think I should do here? We have 25 and 35 are red, and 26 is red, and the grandparent 30 is black. So what is your recommendation? What's the choice I should make here? What's the first step? We have a zig, and the parent and uncle are both red. Yes. Very good. That's exactly right. We recolor. So we're going to have 25 is black, 35 is black, and now we're going to recolor 30 to red. That's 100% correct. Outstanding. What's the next step? Part of the next step was we're going to insert 27. So what should I do here? Let me check the Slack to see if anybody has any recommendations as well. Any ideas on what I should do? I've inserted 27. What do you think I should do here? Yes, in the back. Very good. We're going to rotate and recolor. So now we're going to rotate. 27 is going to remain red. 26 will become black. And 25 will become red. So what's going to happen is we perform that rotation. 26 was originally black and 26 was originally red and 25 was black. We performed the rotation and then recolored the original grandparent and parent. So in the original, we recolored these two, which is why 25 is now red and 26 is now black. All right, last one. We're going to insert 28. What's the first step? Yes. Absolutely right. We're going to recolor parent, uncle, and grandparent. So 25 is red, 27 is red, 26 is black. We're going to change these colors. 25 is black, 27 is black, and 26 is now red. So now what's the next step? Where's my next big issue here? Yes. 30 and 26 are both red. So we have our issue here, and we have a little bit of a zig issue. So now what we can do is we have this scenario. Now we can do our balancing. So now we're going to perform our rotation here. So what we can do is we're going to see that 26 can move down here. I'm going to make sure I do this right. So I'm getting a little paranoid here. 26. Ah, yes. Okay, good. $20. I'm missing one. 20. That should be right. Okay, so what I did is I did that rotation left, and this is the big thing that you'll need to work on the exam. So when you rotate this, we now see that there's a path to every single null pointer in the tree goes through 2 black nodes. And if I remember correctly, this is choice D. Does anybody have any questions about this? Do the same thing. I'm going to check the Slack. And I'll give you a moment. I see people are still taking notes. Okay, I see. So shift 26 up, rotate 26, and recolor. So Lydia, Nick, and Sebastian, very good. Can you explain the rotation again? So that's that last rule. What we have here is we need to maintain a balance, right? So before, what's going to happen is we're going to move. We will make 30's right child, and 26's right child 30. 30 is going to come down here. So we see that 26 is now the root. So we're going to rotate left. 36 is moving up. 36 left child is now going to be 20, and 20 and 26 are going to get recolored. That's the last step. So when 20 becomes the left child, the previous left child of 26, which is 25, now becomes 20's right child. Only these two got recolored. You see how all the rest of the values were the same color? So we're recoloring the original parent and grandparent, And because we're forming this double rotation, 26 moves up, 26 and 20 get recolored. And that's where we get this rotation here. 20 becomes the left child. 25, which was originally the left child of 26, is now going to become the right child of 20. We have maintained the correct ordering, and we have maintained the balance. So please let me know if that addressed your question. All right, the number, one last thing, the number of, okay, first of all, happy to see that I addressed the question. So another follow-up question. Can you explain the null pointers and number of black nodes checked? So this is the important key point of red-black trees. In a red-black tree, the number of black nodes that you go through to get to any null pointer at the bottom of the tree, so children of leaves, will be the same. So for example, if I want to get here, which is below 10, I go through 26 and 20, that's 2, right? If I want to get to these null pointers, 25, 26 and 25, that's 2. If I want to get through here, this null pointer, the left child of 27, I go through 26 and 27. If I want to get to the children of 28, it's a red node, but I go through 26, 30, 27, and 28. The 2 black nodes are 26 and 27. Likewise here, 35, 26, and 35. 30 doesn't count as a black node, it's a red node. So the same number to get through every single one. All right, please let me know if that addressed your question. All right, so let me hop back up here. And so I was gonna start doing some code, but we have 3.5 minutes left. So what I'm gonna do is I'm gonna click on this particular link, and we'll start with the code that I had planned for this lecture at the beginning of Tuesday's lecture. What I wanna do is I wanna go back and do some insertions into this animation to help clarify any other questions. So I'm going to do 25, and what you're going to see is it's going to be inserted, and it's going to become the black node. Next, what we're going to do is we're going to insert 35, and I'm kind of just pulling these numbers up. 35 is going to become a red child. Now I'm going to do 45, and I'm going to press pause, and I'm going to step through. So when I do 45, it's going to become the right child, and now we have this rule where we have the parent and grandparent. The uncle is null, and we consider that a black node. So we have the parent is red and the uncle is black. So now what's going to happen is we're going to rotate. 35 is going to become the new root, and now we're going to recolor 25 and 35. So address the question that was asked a little earlier. This is the last step. We're going to see these get recolored. Now I'm going to insert 55. 55 is going to become the right child of 45. We have 25 and 45, its parent and uncle are red. We're going to recolor 25, 45, and 35. And then sticking with the rule, we're going to go back all the way up to the root, recolor, and now the root becomes black. So now I'm going to insert 40. So 40 is going to become the new left child of 45. Now I'm going to insert 20. That will become here. Now I'm going to insert 10. Let's make 22. We'll make it more interesting. So 22 is going to come in. Now I'm going to get a little zigzag pattern. And what we're going to see here is that 22 is going to come up. 25 is going to become the right child of 22. 20 will become the left child of 22. And then we're going to recolor 22 and 25. So now we get to this case. Now we've moved from case 2 to case 3. Now we're going to rotate, and then we recolor. Now I'm going to insert 21. We'll step forward, and we're going to see that we're going to do the case 1 where we're going to recolor 20 and 25 and 22, like so. and it goes all the way up. Now I'm going to insert 19. And now we're good. I'm going to insert 18. And this will be a good one to end on because this will produce the rotation. Because what's going to happen is we're going to recolor 19, 21, and 20. We're going to see that 19 and 21 are going to become black. 20 is going to become red. Now we have our 20 and 22 rule. And because they're in the same direction, when we perform the rotation, 22 is going to become the new parent, like so. So we rotate over. 22 and 20 and 35, excuse me, are going to be recolored. And now we have reached our balance. Does anybody have any questions about anything we've done so far? All right, next week, we're going to do some coding, and then we're going to go over red-black tree deletion. And then please make sure you're performing your code reviews and progressing on your pre-internships. The praise is flowing from the mentors. They were really happy with how well you did. I'm not surprised. I know Notre Dame students are awesome. They're just learning what we already know. So keep up the good work and have a good weekend. And I will see you all in lab on Monday or in lecture and lab on Tuesday.